Hello everyone and welcome to the channel of Sigma Plus Industrial Solutions. In that video, we're going to continue the discussion about the probability. In the last video, we have defined the probabilities and we have highlighted the main three types of the probabilities, which are the classical, the empirical, and the subjective probabilities. So today we will dig more in the discussions about the probabilities, where we will talk about the intersection and the union of the probabilities, plus the conditional probabilities. And we will give some good work examples so we can practically understand and implement the probabilities in our real life work. Okay. So in many cases, we need to study the probabilities of the intersections or union between different events depending upon the study of the interest. But please remember that the study of the probability is also widely used in the analyzed phase of the dynamic. And here we should start by understanding the basic terminologies of the intersection and the union of the events, the conditional probabilities. So let's start with the intersection of the events. So usually the intersection between two different events means that both events can occur at the same time. So usually I like to refer to what we know is the Venn diagram, where we plot the sample space. So you can see that this square is representing the sample space of the possible outcomes. And in there, I have two possible outcomes. So imagine that I have two outcomes that had occurred, the event of A and the event of B. So you can see that there is an intersection area between the event A and event B, which is highlighted in green, and it can be denoted by A intersected by B as it's shown, right? Okay, so please know that after that slides, maybe 2 slides or 3 slides, we will have a good working example so you can better understand what do we mean with those graphs. Okay, so two events are known to be mutually exclusive in one condition, that they called never occur in the same time or at the same time. So let me give you an example about that. Imagine that you're flipping a coin, and the coin has a tail and a head, right? So it's impossible that when you flip a coin that you will have the head and the tail in the same time, right? So we say that the event of having the tail and the event of having the head are mutual exclusive events, okay? And it can be described with the Venn diagram, where this is the probability of event A and this is the probability of event B, and you can see there is no any kind of intersection area between them. Okay, so what about the union of the events? It could be also described through the Venn diagram. So if I have the probability A and the probability B, so simply the union of the events will be the sum of the whole area for the both events, right? Divided by the total sample size, the sample space, I mean, right? And it is denoted by A united with B as per the shown here, okay? So we have also to understand what do we mean with the complement of a probability event. And the complement of an event is known with the P dash, or if it's an event called A, then A dash. And it's everything's in the sample space that is not A, right? So if I look to the Venn diagram, we can see that this is, okay, the probability of an event A in a sample space. So whatever is located outside the probability is known to be the complement of the probability of the event. And usually, or simply by logic, we can say that PA plus PA dash should be equal to 1, right? Okay, so an example about the complement of the probability of the event. So suppose that you're rolling a single die And we want to know the probability of having a specific event that we need to have the number 3. So the event A, the probability of event A, which is having the number 3, will be equal to 1 divided by 6, while the complement of the event of the A will be any of those numbers that could occur. So it could be 1 or 2 or the 4 or the 5 or the 6. Right? So the probability of A is 1 divided by 6, which is equal to the 0.167 or 16.7%. So the complement of PA dash will be either that you subtract the 0.167 from 1, which is equal to 83.3% or the 0.833, or that if you divide the 5 possible outcomes by 6, it will give you again the same value. So of course, when you add the 0.167 plus the 0.833, it will give you 1. Okay, now let's understand a little bit about the calculation. How do we calculate the probability of the united events? So suppose that I have two events, A and B, and we have here two different scenarios to calculate the probability of the united events or the union of the events. So in the first scenario, if there is an intersection between the both events, so the union probability could be calculated by PA plus PB minus the probability of an intersection between the both events. So the question here is, why do I subtract the intersection? Well, because the intersections had already occurred in the both area A and B, and the probability of the intersections would be included twice. So that's why we need to subtract the intersection between the both events, okay? But in the second scenario, if the both events A and B are mutual exclusives, then the union of the events, the probability will be simply calculating by PA plus PB, okay? So let's take a work example now so we can practically understand how can we implement those simple formula in the real work life. So suppose that you're analyzing the root causes that are leading to malfunction of a garage door opener. So you are a manufacturer for door openers and you want to improve the reliability of your design, right? So you have gathered the historical data for the last 12 months for the repeated failures and studied the probabilities of each defect occurrence as per the shown table. So you have categorized your problems into mechanical or electrical problems, and you have summarized the three different problems that occurred in the door limit switch that occurred 29 times, problems related with the door alignment, which occurred 33 times, and broken spring issues occurred 16 times within 12 months or 365 days, okay? So remember last lesson when we discussed about the empirical probability. So if I want to know the probability of any fault that might come from the door limit switch for the next year, I will simply divide the 29 by the 365 days. Right. So we have also a history log for the electrical problems where the circuit breaker we encountered 5 times problems for the circuit breaker and 2 times for the electrical motor. For those people who are working with the reliability, they are usually doing what we call the fault tree analysis. So here is a simple example of a fault tree analysis where it starts with the measured problem, the garage door is not opening, and it is branched to 2 potential causes, either the mechanical or the electrical, which is also branched further to the components failed, right? And usually it's so important to plot the logical relations between the potential problems, right? So, for example, I can say the garage door could not open due to either a mechanical problem or an electrical problem. And we could have mechanical problem due to either a limit switch problem or a miss door alignment or a broken spring, right? So plotting the logical relationship between the causes of the problem is an important conditions to calculate the probabilities, right? Now, we can start to plot the empirical probabilities of the failure rate of the components, and we have calculated for the mechanical problem. So for the limit switch, it was 0.079, which is approximately 8% probability of limit switch fail within a year. And for the door alignment, we have about 9%. We have about 0.09%, which is approximately 9% probability that we will have an issue related to the door alignment within the 365 days, and 4.5% probability that we might have a spring issue for the door opener within a year. And I can calculate then the total probabilities of the mechanical malfunction, which will be the 0.079 plus the 0.09 plus the 0.045, which is equal to 0.214 or 21.4%. So I can say that the mechanical design system has a reliability that the probability of fail in 1 year could reach to 21.4%. And I have repeated the same for the electrical system, where we can start to see that there is a very minor probability of fail occurrence, either in the circuit breaker or the electrical motor, and with a total probability of electrical malfunction of 1.8% within a year. So with those kind of simple calculations, it helps me to find where is the source of improvement. Where should I start to focus my improvement? Is it either in the electrical or in the mechanical? But indeed, when I look to the probabilities of the events, then I can see that there is a very minor probability of malfunction occurring in the electrical compared with the 21.4% in the mechanical. So indeed, this will help me to focus my improvement to improve the reliability of the design through the mechanical system, right? And I can also calculate the total reliability of the garage or the probability of fail rate within a year, which will be the sum of the probability of mechanical fail or malfunction plus the electrical, which will be equal to the 0.232 or 23.2%, which I can state that there is a probability that the garage door will have a problem of 23.2% within a year. So now we have understood an example about where we are utilizing the union of the events, the probability of the union of the events. But what about the intersection of the events? So the example says that a company assigned a hotline phone service to its customers to pursue the projects which are still under the constructions. It was decided to classify the calls into measure two categories: high urgent calls, and those are the problems that require to send a technical team to the site work, and a low urgent call, and those are the problems that could be solved through the phone calls. The shown table highlights the last 50 calls received by the technical center. So you have in the first column the name of the projects, and you have in the second columns the number of calls per each project, and classified with the low or the high urgency. So what are the requirements here? Well, what will be the probability that the next call will be from the airport constructions and classified with high urgency? And the second requirement is, what will be the probability that the next call will be either from the Dream Star Tower or the Hydra Park Mall and classified with the low urgency? So first step that I would advise you and recommend that every time when you do, you're requested to do probability study, is to make it to simplify it. And how do we simplify it? By drawing our Venn diagram. So the Venn diagram, I can see my sample space, which is mainly divided in two major sections: the low urgency calls and the high urgency calls. And I have multi-events that could happen. The calls that could occur from the airport constructions, or from the Dream Star Tower project, or the Superstore Mall, or the Holiday Star Hotel, and or the Hydra Park Mall. So let's see now how can we solve the probabilities. So the first requirement is to study the probability that the next call will be from the airport constructions and classified with the high urgency, right? So let's start the technique of the Venn diagram. So I'm interested now in, about two events: the airport constructions and the classifications of the urgency, high urgency, right? So this is the first event that I want to study, and it should be a high urgency, right? So what is the first thing that I usually do when I'm solving such example? Is that I will shade all the area, excluding the probability, first of all, the probability of the first event, which is the airport construction. So let's do this. So I start to shade all the sample space and trying to exclude the probability of the event that the call will be from the airport constructions, right? Very sorry if my lines are not so perfect. I'm trying to do my best. Yeah. Okay. So the next step, let's utilize now different colors, and we will shade all the sample space, excluding the interested events, which is the high urgency, right? So I will start to shade the low urgency. Okay. Okay, so what can we remark now? We can see that the only number which is not shaded is number 7, right? So let's use a different color. So we can see that this is number 7. So I can conclude that the probability that the next call will be from the airport constructions and classified with a high urgency is equal to 7 calls divided by the total calls received, which is 50. So 7 divided by 50, which is approximately equal, if I remember, about 14%. Yes, so you can see that is equal to 0.14 or 14%, right? Now, if we want to use the contingency tables to calculate the intersection probability, we can do that. Okay, so we have solved that the first the requirement through the Venn diagram. But if I want to utilize the contingency table, so my first interested events that the call will be received from the airport constructions, right? So I can highlight this row, okay, where I'm highlighting that the call is from the airport constructions. And then we have highlighted, secondly, that the call should be a high urgency. So again, I will highlight the column of the high urgency. And as you can see, that the shaded area, or I'm sorry, the intersection area is the number 7. So from there we can see that we can even calculate the probability by simply dividing the number 7 by 50, which is equal to the 14%, right? Okay. So let's now go to the second requirement, probabilities, right? So the second probability study is mainly to study the probability that the next call will be either from the Dream Star Tower project or the Hydra Park Mall. So you can see the logical relation between the both events, like the last example. So what does it mean? It means that this is a union events here, right? And classified with a low urgency. So that's an intersection with a low level of urgency, right? So where are the probabilities that I'm interested about? It will be the Dream Star Tower project and the Hydra Park projects, right? So let's start first our first step to shade the sample space, and we exclude the both events, which is the Dream Star project or the Dream Star Tower project and the Hydra Park project. And again, my apologies if my lines are not so perfect. Okay, so I start to shade all the sample space, and I just exclude the both events where the calls occur from the Dream Star Tower project or the Hydra Park Mall. Okay, and the next is that the probability that the next call will be low urgency. So the low urgency, which is the left side of my sample space. So I will shade the high level. I will shade everything's located in the high level urgency codes, right? Yeah. Okay. So now, as you can see, we are now ready to conclude the probability result. So I have here number 5 and I have here number 6. So that means that my probability will be 5 plus 6 calls divided by the total calls, which is 50. So 11 divided by 50 equal to 0.22, which is 22% probability. So there is a probability of 22% that the next call will be either from the Dream Star Tower project or the Hydra Park Mall with a low urgency, right? And again, if I want to utilize the contingency table to calculate the probability, I will simply highlight the row where it's related to the probability of the interested events, the Dream Star Tower and the Hydra Park Mall. Right? We can use a different color to make it more visible. And I have classified my interested events is a low urgency. So if I just highlight the column of the low urgency, so I have, as you can see, the intersected points are the 5 and 6. So 5 plus 6 divided by 50, which is the total number of the calls, it's equal to the 0.22 or 22%. So there is a 22% probability that the next call will be either from the Dream Star Tower project or the Hydra Park Mall, right? Projects with a low urgency. Okay. Now, we have understood now the union of the events and the intersection of the events. But what about the conditional probability? Okay, so in fact, there might be too many people who could be confused between the intersection and the conditional probabilities. And the intersection of the two events, as we mentioned before, that both events could happen in the same time, but there is no any kind of dependence relation between them. So what do I mean with that? So in the last example, we have discussed the intersection probability of high and the low level of urgency, right? And we have seen that there was no any kind of conditions that could improve the event occurrence subjected to any other events. It sounds a little bit complicated, I know, but let's take that example to understand the conditional probability. So the example says that it's about a football team that will play a football match, and it's known that the team used to win with the participation of his top scorer player. So there is a condition that improves the occurrence of winning the match subjected to the participation of the top scorer player. So the national team will play against the Blue Stars club, and the coach is still not sure that his top scorer will play the match. So knowing that the team played against the Blue Stars 29 times, the results were as per the shown table. So again here, what you can see is another type of, well, it's a contingency table, in fact. So the team top scorer players, he played 12 times against the Blue Stars. And when he played the 12 times, the team won 7 times and lost the match 5 times. The team played 17 matches without the participation of his top scorer, and the results was that the team won 6 times and draw or lost the match 11 times. Okay, so we are interested in two major events. Event A, that the team win, and event B, that the team top scorer will play the match. And we have the complement of the events, which is A dash, that the team draw or lose the match, and event B dash is that the team top scorer will not play the match. Okay, so the probability that the team will win is, as you can see, 44.8%, and that's simply because we know that the team played 29 times against the Blue Stars, 13 times winning and 16 times draw or losing the match. So that's why we can see that the probability of winning is low, is about 44.8%. And the complement of that event will be simply either to subtract the 44.8% from the 100%, which is equal to 55.2%, or since that we know that the team draw or lost the match 16 times, by dividing the 16 by 29, it will give me the 55.2%. Okay, and the probability that the team's top scorer player will play the match is 41.4%. As we can see that because simply we know that the team top scorer within the 29 matches, he played 12 times, and the number of matches that he didn't play was 17 times. So as you can see, that the probability that the team top scorer player will participate in the match is about the 41.4%, and the complement is 58.6%. So find the probability that the teams wins if the team top scorer players plays the match. Okay. So the first requirement in that example is to find the probability that the team will win if the team's top scorer played the match. Okay, so as you can see, we can simply utilize also here the contingency table to calculate the conditional probability. So when I say that the probability that the team wins under the condition that the team's top scorer will play the match. So I can see that the number of the matches that the team top scorer played is 12. So 12 will be simply my sample space of the outcomes. So I will be interested in that area, right? And how many times did the team wins here is 8 times. So simply, I can say that the probability that the team wins subjected to the conditions of the participations of the team's top scorer playing the match will be 8 divided by 12, right? Which is, as you can see. So in fact, we denote the probability of conditional probabilities of two events by A with a slash to the B, which is equal, as I highlighted, 8 divided by 12, which is 666 or 66.6% probability that the team will win with the participations are subjected to the condition that the top scorer participate in the match. So you can see that there is an improvement in the occurrence of winning the match under the condition of the participation of the top scorer players. And that's the difference between the intersection and the conditional probabilities, right? So the next requirement is find the probability that the team wins if the team's top scorer doesn't play the match, right? So again, it's we use again the contingency table. So my sample space will be subjected to the condition that the team top scorer will not play the match, which is 17 times, right? And what was the second event is that the probability that the teams wins. So this is my second event. So simple as is, we can see that the number of times that the team won was 5 out of 17 match. So we can see that the probability will be simply 5 divided by 17, which is P to the subjected to the B dash, because B dash is the complement event that the team scorer, the team top scorer will not play the match, right? Remember here, event B is that the team's top scorer will play or participate the match. So the B dash, the complement event, is that the team top scorer will not play the match. So there is a 29.4% that the team will win the match in the absence of that player. So you can see now how strongly the impact of that player on the team to win the Blue Stars Club. Okay, so what we can conclude here is about the relationships between the independent and dependent events, right? So there is a dependency relationship between winning the matches and the participation of the best player or the top scorer player. So in the last examples, we says that the events A and B were dependent because the probability that the team wins the football match depends mainly upon the top scorer. And the probability of winning was 44.8% without the participation of that player, and increased to 66.6% if the team plays with its top scorer. Okay, so you can see now and understand the difference between the intersection probability and the conditional probabilities, where the conditional probabilities is focusing on the dependency relationships between two events. There is an event that is helping or empowering the occurrence of the other event, like we have discussed in the participation of the team's top scorer player helping the teams to win and increase the probability of winning from 44.8% to 66.6%. At the end of that lesson, I would like to thank you so much for your good listening and watching, and see you for the next lessons. Thank you so much, and see you.